So as we work through the remainder of Chapter 7, we're going to be spending a lot of time doing proof and trying to prove things that we probably already know to be true, but have not actually proved them to be true. So we've been using what's called inductive reasoning, which is we have lots of examples that show that these ideas or rules work, but we haven't formally proved that these ideas will continue to work and without exception. In the previous lesson, 7.2.2, we actually proved some things to be true about a rhombus. In this lesson, we're going to start off with a rectangle. And so unlike the last lesson, we're going to prove something to be true about a rectangle, but we're not going to divide the rectangle into two triangles. So the proof itself is basically 5 loops. We're going to start with a rectangle, and I'd like you to write down what you know to be true about a rectangle in the next loop and the reason why. And then go ahead and draw the rest of the proof as you see it, and then turn the video back on. So hopefully you've indicated that the 4 angles are all going to be congruent to each other, or equal in measure. They're all 90 degrees, because the definition of a rectangle states that we have a quadrilateral with 4 equal angles. Now that doesn't help me a lot in the next 2 loops, but what I'm going to do is I'm going to expand the proof so you can see the last loop, and then we're going to talk about another type of strategy we can use for proof. So what we're going to try to prove is that ABCD, which is a rectangle, is also a parallelogram. And proof sometimes can be done in 2 directions. So we can start with something we know, and we can say, okay, we know this to be true. And then we can also start at the end of the proof and say, okay, I know that I want to end up with this shape being a parallelogram. So what has to be true before it to be able to say that the shape really is a parallelogram? So I'd like you to think about, based on the picture, what can we say has to be true about the shape to be able to call it a parallelogram? And then how do you connect the fact that these angles are equal to each other to be able to prove that these 2 statements here have to also be true? So how do I connect them? So sometimes we do proof in both directions, and the idea is hopefully when we get to the middle, we'll be able to connect these pieces with some kind of rule, some kind of proof that we've already done, or some kind of definition. So when you're finished, turn the video back on and let's see how you did. So to be able to say that ABCD is a parallelogram, then that means that line segment AB and line segment CD have to be parallel to each other, and AD, that segment, and BC also have to be parallel. But the question is, how do I connect the fact that I have 4 equal angles with the idea that we have 2 sets of parallel sides? So back in Chapter 2, we talked about parallel lines. Anytime you have parallel lines, when you look at the angles are either, when we have parallel lines, the angles are either equal to each other, or they're supplementary. They got to have 180 degrees. So we have 4 right angles, and I need to say that those lines are parallel. So I'd like you to think about which of our rules from Chapter 2 can I use here to be able to connect the equal angles of a rectangle to 2 sets of lines being parallel. And when you're finished, turn the video back on. So you basically have a couple options. We have alternate interior angles, which we don't have in this picture. We have corresponding angles, which we don't have in this picture. And we have same side interior angles, which we do have in this picture. Again, we also have same side exterior angles. We also have alternate exterior angles. But angle A and angle D would be considered same side interior angles. And because they are supplementary, keep in mind, when you have parallel lines, they're either equal to each other or they're supplementary. Because they're supplementary, that means that line segment AB and CD have to be parallel. So the reason here is that same side interior angles are supplementary. And when that happens, we have parallel lines. I can use that justification not only on the loop on the left, but I can also use the same justification for the loop on the right, because this angle at A and this angle at B are also a pair of supplementary angles. And because they're supplementary, as same side interiors, AD and BC have to be parallel. So go ahead, and the last problem that I assigned for lesson 723 is just asking you to decide if the triangles really are congruent, and if they are congruent, by which of our reasons. If you have any questions, let me know.